Hi, I'm Jacob. I'm going to give you a quick overview on how we're using op amps in a very simple way to be able to record small signals from the brain. So particularly in a neuroscience application, we're often dealing with signals that are not only small in terms of voltage, but they cannot source a lot of current. So we would say that they have a very high output impedance. So these are terms that you've likely already talked about earlier. So just as a very quick recap, here's an equivalent model of what a tetrode recording a neural signal next to a neuron might look like. And we've abstracted here the configuration of the tetrode into an equivalent circuit that has a resistive and a capacitive coupling. The details of that don't matter so much. The gist of it is that the tetrode cannot provide an arbitrary amount of current because it's just a very small capacitor, for instance, coupling it to the voltage emitted by the neuron. The fact that the neuron itself also might not be able to provide an arbitrary amount of current, of course, is also true. So in any way, we then have the electrode itself that provides some type of resistance, and then we have a long wire. The wire also acts as a capacitor, as you talked about. So there's a couple things happening here that affect our ability to just translate the voltage that comes out of our electrode or is present at the tip of the electrode to our measurement. And even though we're talking about tetrodes here, where our current is a capacitively coupled current, the same exact reasoning in electrical terms applies to ionically coupled electrodes where there's an exchange of ions, or to electrodes like an EEG. So let's look at this in a circuit simulator and understand a little bit what the problems are that are arising from this. Here's a circuit simulator set up with a fake neural data source. In this case, it's just 60 Hertz, which is a bit of an odd choice, but let's just assume that's what we want to record. Then we have an equivalence resistance for our electrode here for 300K. It doesn't really matter. Then a wire going up to our computer. And here I'm modeling the long wire that goes to the computer with a 1 ohm resistance and a 1K leakage. And then the other thing that this circuit does, apart from providing us with some model of a cable that needs to be driven, is we're also modeling the fact that maybe the computer or amplifier or digitizer in the end itself also needs a little bit of current to run. So let's just see what happens. So the output from here should be 2 volts. So let's see what comes out the other end. So let's run this. And we see that we have basically 0 volt arriving at the computer. And the reason is that the output impedance of our system, determined by the 300K resistor here, is relatively high. But the input impedance of our system, in this case, even the cable itself, is relatively low, which you can see there's a 1 ohm resistor here and a 1K resistor making a voltage divider. And in the simulator, it's very nice. You can see what the current is doing. So first of all, you can see that there's a decent amount of current flow down here to ground. Because the amount of current flow, we have a large voltage drop across this resistor here. So that's just straight up Ohm's law. And you can see on the left side here, we have 2 volt. But as soon as we step on the right side of this resistor, which is the tip of our electrode, there's basically nothing left. So this is just with resistors, and we talked about capacitive coupling and capacitive losses earlier on. So let's just rebuild this circuit, and I'm just going to switch out these resistors here with capacitors. So now you can see that basically the same thing is happening. The reason for that is that depending on the frequency of the time-varying current, whether we put resistors or capacitors in terms of impedance, you can very broadly think about as being almost the same. The basic problem seems to be that we're drawing current from our source, and drawing current is not good because it distorts the signal. In this case, it distorts it to 0. And as we've talked about before, a op amp has this nice ability to not allow any current to flow into its inputs. So let's just remove this piece of wire, and I've already set up the negative feedback here, and instead put a unity gain, so no amplification, right? Non-inverting op amp. So now we still have the voltage on this side and the voltage on this side of the op amp exactly the same. But what we have changed is that there's no more current flowing in. And that means that we're not distorting the voltage at the input. And so if we reset this, you can see that now basically the input and output is exactly the same because this resistor here, this capacitor, does not distort the measurement because there's no current flowing. The same exact reasoning applies when we go back to the resistive case. So now we have our signal back. And this is entirely due to the fact that we're not drawing any current from our electrode. We're just looking at the voltage without drawing current. It's obviously not 100% true in the real world. This is a simulation, but we're drawing an extremely tiny amount of current in the real world. So to recap, drawing current from our electrode is an extremely bad idea because it distorts our measurement. In real world terms, it distorts our measurement even with a couple meters of wire to get from a mouse to a computer or something. It distorts it to zero. And the solution to that is to just not draw any current from the electrode. And we're doing this by putting a non-inverting op amp here, which, as you talked about, doesn't take any current into its input, but yet has the ability to provide the same voltage. So one way to talk about this in the language of impedance is that we have a high output impedance source, which is our tetrode in this case, and we have coupled that to a very high input impedance input on the head stage now, on the buffer amplifier. And on the other side, we can say that the amplifier has a very low output impedance, which means it'll provide however much current is required for keeping the voltage at the output the same as the voltage at the input. This means that it can drive this cable, even though this cable is a pretty hungry consumer of current, it can drive that cable to maintain that voltage up here. And there's still some voltage drop here, of course, because there's a voltage divider that the amplifier can't do anything about. But the voltage coming out of the op amp and the voltage at the input terminal of the op amp are the same, and it's going to provide as much current as is required for that. So I think that concludes this video. So let's run this. us with some digitizer in the end itself also needs. And we see that we have basically 0 volt arriving at the computer. And the reason is that the output impedance of our system, determined by the and that means that we're not distorting the voltage at the input. So if we reset this, you can see that now basically the input and output is null in the real world. Just not draw any impedance is that we have a high output impedance
Um, I would like this setting where we watch on our own and then watch together or you explain. Also, one doubt I had was the tip of the electrode is exposed, right? The rest of the electrode is insulated. So all the signal you get is from the tip.
Yes.
However, in the last class when we were looking at the silicon chips, the other type of electrode, not the electrodes, those silicon shafts, they had perforations all throughout their body, right? Through the length of the silicon. In that case, how do you know where you're getting which unit signal from?
Yeah, I'm okay with that. We can watch independently and then we can sort of discuss together. I had a question on this one. So the idea behind put inserting an op amp amplifier was was that the sort of the current drawn is minimal, so that the voltage on the other side is roughly the same as at the site that we are recording from. But even after that, there will be at what point are we connecting op amp? There will be sort of a resistance before and after the op amp, right? Some intrinsic resistance of the solution or of the medium. I see. Yeah, but before that, there will be some sort of loss of current. Is that true? I see. I see. But so far, before the amplifier, there is no sort of resistance of any medium that leads to some voltage drop. I see. Yeah. Okay.
Hey, one more question I had was, why is, I mean, is there a rationale behind deciding K's value to be 10 raised to 16, or what was the rationale?
Yeah, and there might be some limitations like in the microelectronics industry that they can't make it like 10 to the 8 or something, right? Hmm.
So now that we've talked about buffer amps, let's talk about differential amps and why they're important real quick. As you've talked about, in a lot of cases, you'll be recording from an animal. Let's just put a tetrode in here somewhere, recording from some neuron. And the data that you're typically interested in are spikes from a neuron, let's just say in this example, although exactly the same considerations apply to EEG or, as you'll do in the exercises later, EMG. What happens usually is that the signal of interest, in this case spikes, is overlaid on a bunch of environmental noise. So for instance, you have power lines on the wall, your cell phone, computers, what have you. There's a bunch of electrical noise that's coupled into your animal. And in most cases, the most prominent one is the 60 or 50 hertz mains power coupling in. So what that means is that on top of the signal of interest, let's say your spikes, you also have a big noise signal, and those are superimposed. So what you're actually getting out of your tetrode here is the noise signal, on top of which there might be the signal that you're interested in. One way to get around that is to put a second electrode, let's say just a reference screw or something, next to it. And now we set it up so that the reference screw is in good electrical contact with the animal. So it's picking up the same overall noise signal as the tetrode, but it's not expected to be sitting next to any neurons. It should have the same noise characteristics or pick up the exact same noise signal as the tetrode, but it is missing the spikes that we pick up on the tetrode. So now if we had an amplifier that, instead of just buffering and amplifying the signal like we talked about before, that could take the difference between those two, what we might be left with is a signal that is now only the spikes. So here we have the same situation set up in the circuit simulator, where we have our tetrode signal comprised of the background signal and spikes, and the reference signal that just has the background signal. And here the background signal is a 60 hertz, 5 volt peak-to-peak waveform, and our spikes are 10 millivolt square waves. As you can tell, they're too small to see. And so here I've also added the output impedance corresponding to something like a tetrode and some input impedance on our PC amplifier. So let's just real quick recap what we saw last time. We can't just connect this input to the computer. You can see that the output signal here is extremely tiny. And last time we solved the problem by putting a buffer op amp in, and to stop it from saturating, we added feedback. So now we have removed the problem of drawing current from our electrodes. We have an amplifier with a nice high input impedance, but obviously this is just one input and we don't get rid of our common mode noise here. Now you might think, to get this thing to compute the difference between two signals, which is what we're interested in, you could simply connect the two signals to the positive and negative inputs and see what happens. So let's try that out. So what happens is that there is no negative feedback, and the amplifier is basically acting as a comparator, and it's just telling us which one is higher than the other. And even though this is happening when the spikes happen here, in real world terms, that is basically useless. So how do we simultaneously take the difference between the two inputs and have negative feedback to give us a non-infinite gain? And so the answer is that we're going to use a voltage divider to provide both the signal of interest and the feedback signal to the negative input terminal. So let's see what that looks like. And so now we see that the output looks very much like the input, but it seems to be inverted. When you reset this, you can see that the input goes to plus 5 volt immediately, and the output swings to minus 5 volt immediately. So what is happening? The op amp is providing whatever output it needs to keep the difference between the positive and negative terminals at 0. This is true even with this feedback with a resistor in it. But now, because the negative input, which it tries to keep at 0 volt because the positive terminal is grounded here, right? It's the difference between those that counts. Because that negative input is sitting at the middle of a voltage divider with equal resistors on both ends, where one side is our input and the other side is the output, in order to keep that at 0 volt as dictated by the ground on the positive input, it needs to provide exactly the reverse of that. And so this is what's called just an inverting op-amp. And so now there's one weird thing that is happening that is worth talking about, which is that the inputs to the op-amp now are both at 0 volt. So if you measure this, this is actually true on your breadboard. And so what's happening is that this node that I'm highlighting here, that's called the virtual ground node, because the op-amp is keeping that at the same voltage as ground, 0 volt. And this is a little bit confusing, because how can the thing work when both inputs are at 0 volt? And the answer to that is evident in the simulator. There's a bunch of current flowing, and basically what the op-amp does is it provides an output voltage that drives enough current through here to keep this virtual ground node at 0 volt, and the result of that is that the output is the input times -1. So there's a video that we linked that gives a more in-depth description of that and derives some of the formulas related to this and the gain that you should look at if you're interested. So for now, let's play around with this a little bit and see, for instance, what happens when instead of the ground, we connect something else to this input here. So for instance, we could imagine adding a static voltage. And so you can see that when I add a voltage here, I can move the output up and down by some amount. And so now the next obvious step would be to just take our signal of interest and put it in here. So let's see what happens when we do this. And so now this doesn't seem to quite work. And the reason for that is that the op-amp does whatever it needs to do to keep its two inputs at the same voltage, not to keep this signal here and this signal here at the same voltage. The virtual ground node sits in the middle of this one-to-one voltage divider in our case. So in fact, it is seeing half influence from the output of the op-amp, and that's half influenced by the signal. So in order to make this situation symmetrical, we now also need to divide the other input by 2 to provide a one-to-one voltage at the input, where if we have the same voltages here for our common mode noise signal in this case, that is going to cause the same voltage on the positive and negative terminal, so it can be subtracted. So to do that, we're simply going to replicate the voltage divider, and there we have it. And so now, once this thing rescaled, we should be seeing a 10 microvolt spikes on the end. Voila. So now we have a differential amplifier that can get rid of a common mode noise, this huge 60 Hertz oscillation. And by computing the difference between the reference signal and the, in our case, tetrode, whatever signal, we can get the signal of interest isolated. But now this comes at a bit of a cost, right? So in order to do this, we have to add these voltage dividers here. Let's see what happens when we put our simulated electrodes back in. So I put in 300K just to pretend that those are tetrodes, and our signal is basically gone. And this is because we're now drawing so much current through these voltage dividers here that the input impedance or the impedance of the electrode is not enough to drive that, and we're distorting the signal. For instance, what happens when instead of the ground, influence from the output of the op-amp, and that's half influenced by the signal. So in order to make this situation symmetric, mode noise, this huge 60 this input here.
Maybe it is somewhere like near the neck or somewhere outside the outside CSF and outside meningit.
Hi, I'm Jacob. In this so in the last video, Hi, I'm Jacob. In this video, I want to give So in the last video, we've seen how we can use a differential amplifier like what you see here in order to get rid of a common mode noise, for instance, environmental noise from mains power or really anything else. It could be motor noise, could be motion artifacts from the animal, anything where you can have a reference signal that picks up the noise, but not the signal of interest. In theory, a differential amplifier like what you see here is great for that. In practice, as you see here, the amount of current that this thing is drawing means that we're massively distorting signals or eliminating signals, as you can see by the voltage drop across these resistors that are stand-ins for tetrodes, for instance. Our input impedance, you would say, to this amplifier is lower than we would like because we're drawing current here. How can we solve this problem? Basically, we're in the same situation as we were right at the beginning of the course when we thought about just connecting a tetrode to a long wire, where we saw that the wire alone had enough input impedance to distort the signal, and we used a buffer op-amp to amplify the signal's current driving capacity to drive the cable. So why don't we do the exact same thing here? and just buffer these signals before they go into the differential amplifier here. So to do that, I'm just going to grab two op amps. And so here I'm going to set them up in the non-inverting configuration. So one of them is the plus on top, the other one is the plus on the bottom. That's just for aesthetics. And then we need to wire them up with negative feedback because we just want buffering out of them. And so now we have a two-stage system where we have a pair of unity gain, non-inverting buffer op amps that have extremely high input impedance because their non-inverting input terminal is connected directly to the tetrode. And their output now goes to the differential amplifier. And the differential amplifier takes care of the common mode rejection. So let's see how that works. And you can see that we're getting perfect 10 millivolt spikes out of here, and we're not drawing any current from the input. This is basically the idea behind an instrumentation amplifier. So now let's very quickly go over some details of how to set something like that up in real life. And by the end of this, we should be able to understand how to use the instrumentation amplifier chip that comes as part of your kit. So far we've seen this topology with two unity gain buffer op amps at the input and the differential stage at the end. So let's begin by adding a little bit of gain to this, because we don't just want a one-to-one signal with a 10 millivolt output spike, but we want to bring that up into something that we can digitize. Okay, so I just rearranged things a little bit here. And so now let's add gain to the buffer input stages here. As before, we will do this by just adding a voltage divider to the negative feedback to make the amplifier work proportionally harder to get its input terminals to the same voltage. And so now with a one-to-one voltage divider, we see that we doubled the gain of the whole system by making the buffer input stages that were previously unity gain into a gain stage. In theory, this could work, but now let's imagine that these are physical op amps that have slight imperfections. So for instance, let's imagine that these resistors here are not perfectly matched. So I'm going to take this resistor, and instead of 1K, let's put 1.1K. That's not a huge difference, but we can see that we, for instance, we're put stage bit of gain to this because we don't just want a one-to-one signal with a 10 millivolt output spike, but we want to bring that up into something that we can digitize. Okay, so I just rearranged things a little bit here. And so now let's add gain to the buffer input stages here. As before, we will do this by just adding a voltage divider to the negative feedback to make the amplifier work proportionally harder to get its input terminals to the same voltage. And so now with a one-to-one voltage divider, we see that we doubled the gain of the whole system by making the buffer input stages that were previously unity gain into a gain stage. In theory, this could work, but now let's imagine that these are physical op amps that have slight imperfections. So for instance, let's imagine that these resistors here are not perfectly matched. So I'm going to take this resistor, and instead of 1K, let's put 1.1K. That's not a huge difference, but we can see that we created a huge problem, which is that our entire output signal has now been taken over by the common mode noise again. And this makes sense because the entire trick of the system previously rested on the fact that if we had the same signal on the common mode here, that it would create the same voltage on the input terminals to the differential amplifier in the end, and that those would be subtracted out. And if the gain now between one and the other is not perfectly matched, then we have a problem. So how can we solve this? There's a very simple little trick here that really amounts to just getting rid of these voltage dividers between ground and the feedback for the two input stages of the instrumentation amplifier, and instead just connecting them together so that one can serve as the reference for the other. So let's just see what happens when we do this. So now, magically, everything works again, and we get gain, but we also get perfect common mode rejection. And so let's take this a little bit further and like really mismatch these things. So I'm going to put 2K here. And now my gain has changed a little bit, but somehow, even though these resistors are now as imprecise as they can be, the common mode rejection ratio is still perfect. There's another nice thing that happens here, which is that there's this one resistor in the middle here that if I, let's say, mate that resistor so that us as users, we can change it, we can use that to change the gain. So I just set it to 2K, half the gain. This resistor in the middle that's highlighted now is commonly known as the gain resistor. And on the instrumentation amplifier that comes as part of your kit, this is referred to as R gain. And that's the one where we get to pick the amplification gain of our instrumentation amplifier. But for now, let's just go through a simple schematic overview of why this topology does so well. So let's consider the case of us having only common mode noise from here and here. And we want to understand why under no circumstances can this common mode noise elicit a voltage difference on the inputs to our differential stage. To understand this, we literally just need to follow the current, and it's going to become relatively obvious. The first thing that we know is that because of the feedback on these input op amps, the voltage on the positive and negative input is the same, which means that if V1, one of our voltages, is the same as V2, which is the basic condition for it being common mode noise, then the voltage is the same here, and then the voltage is also the same here. And we know that there is no current flowing in and out of the inputs of the op amp. So there's no current flowing around here. Similarly, there's no current flowing around here. So if there's no current flowing here, that means that there is no voltage drop across this resistor, and there's no voltage drop across this resistor. And so assuming that these resistors are the same, the only voltage drop in this whole loop here is now induced by the voltage differential between V1 and V2 across our R gain. So if V1 equals V2, then the voltage in this loop, because there's no current here, is 0, which means that assuming that our gain stage is matched, which is an easier task because now we're dealing with an amplified signal, we get a very good common mode rejection. If V1 is not equal V2, now we can understand how much voltage differential that is inducing in this loop by just looking at our gain. And so if you want to understand this in more detail, have a look at the handout. There's links to more in-depth documents, and you'll find a lot of material about this online. But this is the basics of what makes an instrumentation amplifier so great. So now that we've seen this, I'd like to show you one more little scenario that explains why we would want high input impedance on our amplifiers. So let's go back to a simple differential amplifier that, as we've seen, has pretty terrible input impedance because of all these voltage dividers here. And consider what happens when we have actual electrodes with their own impedances. So now we're in a situation where not only do we attenuate the signal quite a bit, but also because of the terrible input impedance of the amplifier, we have another problem. And that is if our, let's say, tetrode has a 300 kilo ohm impedance, but our reference screw, let's imagine this up here is our reference screw, has not 300, but 305 kilo ohm, what happened? Not only are we dropping the signal across this electrode resistor here because of our input impedance, because of the current we're drawing, it also now matters a whole bunch how much we're dropping, what that impedance is. So if our reference electrode is not exactly matched to our recording electrode, we're not able to see the common mode signal across those, so we cannot subtract it out. An actual ground screw might look more like this. So now we have a problem. Now we can look at the same situation with our instrumentation amplifier. This is obviously an idealized version of one with absolutely no current running in. But now we can take these 300 kilo ohm electrode impedances and do whatever we want with it because there's no current flowing in, so there's no voltage drop across the electrode impedance. So we can have an extremely low impedance reference and an arbitrary, theoretically, tetrode impedance and still get nice common mode rejection. So that's another reason why high input impedance matters. Get nice common mode rejection. It also now matters a whole. If our reference electrode is not exactly matched to our recording electrode, we're not able to see the common mode signal across those, so we cannot subtract it out. An actual ground screw might look more like this. So now we have a problem. Now we can look at the same situation with our instrumentation amplifier. This is obviously an idealized version of one with absolutely no current running in. But now we can take these 300 kilo ohm electrode impedances and do whatever we want with it because there's no current flowing in, so there's no voltage drop across the electrode impedance. So we can have an extremely low impedance reference and an arbitrary, theoretically, tetrode impedance and still get nice common mode rejection. So that's another reason why high input impedance referred to as R gain, and that's the one. I'll give you a quick overview of and then among all the channels, and then you have, and that is we typically all situation in the circuit simulator. This guy here should be up and down. The situation became much worse because now our impedance of the ground screw has gotten high enough that they make has half the number of channels but avoid splitting. To simulate this, I'm taking a resistor and I'm just grounding the Faraday cage here. So mind you, this is so here just to give us things are done. And practically the output of the whole system. Hi, I'm Jacob.
Yeah, yeah. Two and two, or is it just one coming out?
Two inputs and one.
Yeah, yeah. I think it's a easy one. We can watch together.
Hi, I'm Jacob. In this video, I want to give you a quick overview of what ground and reference mean with regard to electrophysiology, mostly extracellular electrophysiology, but really it's the same even when we talk about something like an EEG system or an EMG recording. You might have seen on the EIB, electrode interface board, or somewhere on your EFIS system that there's a ground connection, but there's also this ref connection. This is what this looks like on our shuttle drive, EIB. This is what this looks like on a head stage. So there's a ground input and a ref input. So what are these good for? At the most basic level, when you think about the amplifier that sits on the head stage, and this is an instrumentation amplifier in the broadest sense of the term, you have a positive and a negative input. And then you have the ground that connects to whatever reference level you're using. So this could be the laptop that you plug into it, really whatever is the ground level. So what this means is you have an extremely high input impedance here and here, and you have an extremely low one down here. If we have a weak signal from a tetrode or something like that, we can conceptualize as having a very high output impedance, then we can still record from that just fine because we are not dropping any voltage across this resistor because there is no current flowing in and out of here. So the same goes for our reference signal, of course. So if we have some reference electrode that also has a relatively high impedance, then we can still record that signal. Whereas our ground input is able to sink or source as much current as is necessary. So as we'll see, the ground input is really good at one thing, and that is bringing whatever it is connected to close to 0 volt. The reference signal is subtracted from the tetrode signals, in theory, in an exact one-to-one fashion in an instrumentation amplifier, as you've seen in the other videos, with exactly matched input impedance, which gives us very good common mode rejection. Now, in reality, the situation is a little bit different often. So here is the spec sheet from the Intel RHD chips that we're using in the OpenEFA systems, and like a lot of other systems are using those. So when we zoom into it a little bit here, we can see that the reference input is shared among all the channels. And then you have the electrode inputs going into the differential amplifiers here. In practice, the input impedances are not perfectly matched, but it's certainly a higher input impedance than the ground input. So what does this mean in practice? So let's imagine you have a mouse that you're recording from, and you have some tetrode in there, and then you have your amplifier. The amplifier is connected to a computer. You would first have the tetrode connected to the input of the amplifier. And so now you need to have some reference signal, right? Because the animal sits in some environment in which it is subjected to a lot of common mode noise. So you could imagine that you have, for instance, a lot of 60 hertz noise floating around everywhere. So that noise is all over the animal. And to get rid of that, what you want to do is you want to have a reference electrode somewhere on the animal that only picks up that 60 hertz noise or motion artifacts, whatever other noise you might have. But then you have your tetrode that, in addition to that noise, also picks up your spikes of interest. And now we have a reference electrode, let's say a screw somewhere. You're probably familiar with the term ground screw. So now that could connect to the other input. And now, because of the nice common mode rejection that we talked about in this instrumentation amplifier here, the output of the whole system ought to be just the spikes with none of the noise. In this situation, we have completely ignored the ground, and we have just said, okay, let's use the common mode rejection properties of the instrumentation amplifier. Just label this ref, this is our reference signal here, and then our tetrode signal here, tetrode. The first problem that happens here is that the animal, if it's sitting in a plastic box or something like that, could very easily be at, let's say, 1,000 volt or something like that, because it's just picking up static electricity from the environment. That is 1,000 volt relative to whatever your computer is plugged into. That's the first problem. And so in the lecture on instrumentation amplifiers, we'll get into why an instrumentation amplifier, even though it has very good common mode rejection, cannot very easily deal with potential difference, right? At some point in here, the inputs need to be referenced to the outputs, which are ground referenced, so we can't have an arbitrary input range on our amplifier. In fact, most amplifiers have a relatively small input range, so if you had something like that, you would saturate the amplifier like crazy. So that's the first reason why this might not be a good situation. The other consideration is that the ground level is optostatic. In almost all cases, practically speaking, you are better off if you start getting the animal that you're recording from to ground level. So you want a situation where the animal is somewhat close to ground, and now you can record your spikes. To do that, practically speaking, what most people do is that they just take the ground and they connect it to the reference. And so now what happens is that the ground screw, or the reference screw, whatever you want to call it, so now it makes sense why it might be called ground screw, is also pulling the entire animal to ground, whatever that might be, even if it's going up and down. Imagine a very bad scenario in which your ground level is fluctuating relative to the rest of the room. Then the ground screw would be charging and discharging the animal, let's say at 60 hertz or something, hopefully taking the entire animal up and down to that level. And so now, because the reference input to your instrumentation amplifier is also tied to ground, you're basically just bringing the entire animal to the level of your reference input. So now you can also understand why it's not a big problem that on the in-time chip, for instance, the input impedances aren't perfectly matched, because we're not really making that much use of them, because now the entire animal for our purposes is sitting at 0 volts. So now our tetrode signal is just relative to that, and we're happy. So that's how most recordings are done. And practically what that looks like is that most people on the EIB just connect them together and call it a day. So there's one more interesting and practically important thing when it comes to grounding animals or ourselves in the case of EMG, EEG, what have you. And that is we typically also put ourselves or animals in Faraday cages. And as we talked about, the input impedance of the inverting input of our amplifier doesn't matter much because it's basically being fed by the infinitely low output impedance that is ground, right? Ground can source or sink as much current as is needed. And so now let's imagine that there's a room or a cage or something like that. And now the room or cage could be at a different potential. So let's imagine, as we talked about before, there's some variation in the ground that our computer is on. This could be from the computer's power supply. It doesn't really matter. But there's a slightly different voltage fluctuation present in the room. This could simply be that the cage that you're doing your recording in is not perfectly grounded, that it has its own capacitance or something along that line. So now the animal is sitting in an environment in which the charges that surround it are constantly flipping back and forth. So this is not quite the same thing as shielding the animal from environmental fields, which we also do. This is a separate topic, right? So the interior field that is in this box now, because it's a Faraday cage, is homogeneous. So there is no problem with charging part of the animal differently from another part of the animal. But instead here, we're just talking about the case that the electrical potential of the cage is not the same as the electrical potential of the animal. So now what you're asking your ground screw to do is to bring the animal up and down to the ground level that is dictated by the ground of your computer. So that's this path here. And you're hoping that that's enough to bring the entire animal to that level. But at the same time, you have some other voltage from the outside, and the animal is either resistively or at least capacitively coupled to the environment. And so that's now also trying to bring the animal to that level. So the animal is a bit of a little voltage divider. You can think about it like that. So depending on how good the impedance of your ground screw is, so you want it to be as low as possible, the ground screw might very well win. So you might get a good recording that way. But in a lot of cases, you also have the problem that the tether going down to the animal is a bit of a resistor. Now, the impedance of the ground screw going to ground that you're trying to bring the animal to ground level with is not low enough. A simple solution to that is to just take the entire cage and ground it. And so now everything is more or less at the same level, and the ground screw can do its job more easily. So here, just to give us another way of thinking about it and a bit of intuition, a simple solution to that is to just take the entire cage and ground it. And so now everything is more or less at the same level, and the ground screw can do its job more easily. So here, just to give us another way of thinking about it and a bit of intuition, I built the exact same situation in the circuit simulator. This guy here should be familiar to you by now. This is just our instrumentation amplifier, and previously we had considered a situation like this. On the left side, you have a common mode noise, and then we add to that our spike signal here, and we're using instrumentation amplifier to separate out the spikes that, despite being small, are only present on one of the inputs and not on the reference input. So this would be the reference input up here. This would be our channels, and then wherever we have a ground symbol would be our ground. Down here, I put a model of a mouse in a cage, and this is basically just a bunch of resistors stuck together. Obviously, that's not what a mouse looks like, but electrically, for our purposes, is a sufficient approximation when we forget all the capacitive and inductive components, let alone any of the biology. And then the mouse is coupled to the cage with some simple capacitor here. So I'm going to move my neuron down here into the mouse, and I'm going to apply the noise to the cage. And now we're going to connect our tetrode to the mouse. And so we could, for instance, begin by just grounding the reference and see what happens. This obviously doesn't work well, and all we're seeing is some saturating noise signal because the animal is being pulled up and down by the environmental noise through the cage, and we're not subtracting that out. So now let's do a more realistic example, and let's see if we can bring our mouse to the ground level of our system. Now, mind you, here this ground level is perfectly zero. That could be your computer ground, might be a little bit different from the ground on a different outlet in your room, or from the ground that you would get if you went outside, dug a hole, and buried a long wire. So let's connect ground and ref together. So now we've connected a ground screw somewhere on the animal, not extremely close to the tetrode, but close enough so that our ground reference input can bring the animal to our ground level, and we can get some recording. Though you see there's still a lot of noise here. So this is a fairly realistic situation that you might be familiar with. So now let's go one step further and make it a little bit more realistic. And instead of having a ground screw and a tether going
Hey,
to
I
the
was
recording
wondering,
system with an
we have screws on top of our boxes. When you ground the box, those screws are taken care of, right? Because you said there can be nothing metallic in the box. No, nothing metallic. That the animal is in contact with. Correct. So that is grounded. But what about the handlebar? Everything should. So why doesn't that take care of liquid? Liquid is connected.
arbitrarily low impedance. Let's imagine we have maybe a ground screw that's not perfect, or just a very long tether here that has some resistance. And so let's see what happens now. And you can see the situation became much worse because now our impedance of the ground screw has gotten high enough where it cannot force the animal to ground level, and instead the animal is being pushed up and down by the environmental noise. This could happen just because the cable is long. This could happen because your ground screw is not good. This could happen because your ground screw is too far away to where you're doing your recording. One thing we can do in that situation is, instead of trying to bring the mouse to the correct level more aggressively, we can try to reduce the impact of the environmental fluctuation by making the cage closer to ground level. To simulate this, I'm taking a resistor and I'm just grounding the Faraday cage here. So mind you, this is the same ground as this. So in real life, this would be the alligator clip with the long wire that goes from your acquisition system's ground input to the tinfoil on your Faraday cage. So let's see what impact that has on our recording. You can see that because of the voltage divider that I put here, so basically I have not assumed that I've done a perfect job at getting the environment to ground level. It has made our recording much nicer because now our ground screw doesn't have to work quite as hard in bringing the animal to the correct voltage level. So what are situations when you might not want to do this? So you could imagine that you're in a situation where you know that there's a lot of noise, and that even if you have a scheme where you are grounding the animal to your reference level through something like a skull screw somewhere, So now you could have a dedicated ground screw that is just there to bring the animal to ground level. And now you could have a separate reference electrode, a tetrode that you put into white matter. Some people use a tetrode that has been partially de-insulated to provide a lower impedance reference. And you put that somewhere close to where you're recording, but not all the way there. So now you get the ability to get rid of most of the voltage fluctuations of the animals with your ground screw, but you're additionally taking advantage of the fact that you can have another local reference that you subtract out from the signal of interest on your tetrodes. I'm saying tetrodes, but really this applies to any kind of electrode. For this to be maximally efficient, you might want to use a truly bipolar instrumentation amplifier where the input impedances of the positive and negative inputs are met. So in the case of Intan, there is a chip that they make, has half the number of channels, but avoids splitting the reference signal to give you a matched input impedance, for instance. You need to know what your signal is, right? So if you do this and you want to record an LFP signal, the signal that is present on your reference electrode is going to be contaminating or it's going to be showing up in an inverted manner in all your other signals. This is the kind of thing where, for instance, if you do EEG, people pay a lot of attention to which electrodes are grounded and which electrodes are used as reference for what, because that really changes the signal that you get out of that. So I hope this made sense, and next time you see the ground and ref inputs on your head stages, it makes a little bit more sense what they're there for. And as always, if you have questions, please ask them in our forums.